Let's do some questions from section 7.3 in the Practice of Statistics, 5th edition. Specifically today we are going to look at questions number 51, 55, 59, and 61. The first question was question number 51, but obviously it refers to question number 49. So I wrote down some key information from question 49. This was about some songs on someone's iPod, and they had the population mean was 225 seconds. The standard deviation was 60 seconds, and then the original sample size was 10 songs. Okay, so we're clearly talking about means here. Notice it says sampling distribution of X bar. So we're talking about sampling distributions of means. If we check out the formula sheet, we know that the mean of X bar, the mean of the sampling distribution of X bar, is the mean of the population. So that's going to be 225 seconds no matter how many, no matter what the sample size is. Standard deviation, however, of the sampling distribution of X bar is equal to the population standard deviation divided by the square root of n. We don't really have to. This is not what this question is asking, but just a reminder, please don't forget to check the 10% condition if you're asked to find the standard deviation. So the original was 60 divided by the square root of 10. They're wanting the standard deviation to be 30 seconds, like specifically. So the original population standard deviation is 60. I don't know what my sample size is going to be, and I'm wanting this to be 30 seconds. So really, we just have to think about what we want to plug into n to make this work. You could do some algebra. You can multiply by the square root of n, then you could divide by 30, and then you could square it to get rid of the square root. You also could just think like, okay, I really want to do 60 divided by 2 here to get 30, and the square root of 4 would give me 2. So n is going to have to be 4 to have a standard deviation of 30 seconds. I really like this question and hope that many of you are watching this video so that you can see the difference in part A and part B. So we're given some information about some bottles that are filled up with cola. They're supposed to have 300 milliliters, and then they go ahead and tell us this information right here about the population. So the population is approximately normal, and it has a mean of 298 and a standard deviation of 3. Like that was given to us for the population. Now, notice that for part A, it says, what's the probability that a randomly selected bottle contains less than 295 milliliters? They are selecting one bottle out of the population. This is not a sampling distribution. It doesn't say anything about finding the mean of a sample. It's just like taking a bottle. Like there's no p-hat, there's no x-bar. I'm just taking a bottle out of the population. So this means I'm not using any fancy formulas or anything. This is like a problem from chapter 2 about the normal distribution. Now, I could find the z-score if I wanted to and then use the normal table, or I could draw my sketch and label it well with the mean and the standard deviation and the boundary, and use the Statlet or some kind of calculator to find the answer, which gives me 0.1587. Don't forget to answer the question. Like essentially everything that I just put right here is like my work, okay? And then I need to actually answer the question and say there is about a 15.87% probability that, and here's where I just always go straight to the question and copy it down. So that a randomly selected bottle will contain less than 295 milliliters. Okay, now look at part B. This is different. This is important to notice that these two are different from each other. What is the probability that the mean contents of 6 randomly selected bottles are less than 295 milliliters? 6 randomly selected bottles, mean. The mean of 6. This is an X bar situation. My sample size is 6. Okay, so it's important to notice the difference between part A and part B. So the mean of a sampling distribution is equal to the mean of the population, so that's still going to be 298. But what changes in this scenario is the standard deviation, because I'm not using the standard deviation of the population, I need to use the standard deviation of the sampling distribution. So it's going to be 3 divided by the square root of 6. Which gives me 1.2247 milliliters. I also realized I just did a no-no. I went ahead and calculated it before checking the condition. So I do need to check the 10% condition before I actually use this. So 6 bottles, I'm sure, is definitely less than 10% of all the bottles filled there. So 10% condition check mark, so I'm allowed to use that standard deviation formula. That's important. So we make sure we check the condition. We have the mean, we have the standard deviation. Now I need to make sure that it is normal so that I can actually do a normal calculation. I didn't have to do this in the first question because I was doing the first question about the population and they told me the population was approximately normal. I also know that the sampling distribution of X bar is approximately normal because the population is. Remember, there are 2 reasons why a sampling distribution of X bar could be normal. The first one is that the population was normal. So that's easy. If that's true, you can just write that down and stop, which was the case for this problem. If that is not true, though, if you don't know what the population is or the population is skewed, you need to have a sample size of at least 30 by the central limit theorem. Notice here, I do not have a sample size of 30. I have a sample size of 6, but it doesn't matter because the population is approximately normal. So since the population is approximately normal, that means the sampling distribution is approximately normal, which means I can do a normal calculation to actually answer this question, which was what is the probability that the 6 bottles have a mean of less than 295 milliliters? So notice the picture looks really similar to the one up top, but my standard deviation changed. So since the standard deviation is smaller, this percentage is it should be smaller as well. You're going to need to type that into a Statlet, type it into your calculator and use normal CDF, or find a z-score and use the normal distribution table. You end up getting 0.0072. And don't forget, all of that is my work, so I need to actually answer the question in words. There is a 0.0072 probability, and I really should say there is about, because everything here is approximate. There is about a 0.0072 probability that the mean of a sample of 6 is less than 295 milliliters. So let's just maybe think about this for a second, the reason why this makes sense. It kind of makes sense that you could randomly choose one bottle and it be that much less, but randomly choosing 6 bottles and finding their average and it being that small when the average is supposed to be 298 is pretty unlikely. Question number 59 refers to number 49. Again, there was some information on question number 49 that I wrote down earlier. The mean of the whole population was 225 seconds. The standard deviation was 60 seconds. And the original sample size was 10. They also mentioned that the population was skewed right, just like in number 40. Question A says, explain why you cannot safely calculate the probability that the mean playtime X bar is more than 4 minutes for a simple random sample of 10 songs. All right, so we're talking about an X bar situation, and we're trying to find mean. The issue with that, we're trying to find a probability. The mean is this. So essentially they're asking us to use a normal curve to find a probability. When you see find a probability, I want you to think use a normal curve. So basically this is kind of asking indirectly, is this approximately normal? And the thing is, it's not. So we can't. The answer to this one is no. The reason is because, first of all, n is less than 30, because, 10 is less than 30. So the CLT is not met. Remember that the CLT, central limit theorem, only applies to sample means, and this is a sample mean situation, X bar. CLT is not met. The other condition that's a possibility is if the population is normal, but we're told that the population is skewed. So this is not normal, which means we can't find the answer. So you just stop. Isn't that lovely? But for part B, suppose we take a simple random sample of 36 songs instead. So explain how the central limit theorem allows us to find the probability that the mean time is more than 240 seconds, and then calculate it. So obviously here 36 is greater than 30. So the CLT applies. Which means that we're talking about a situation here that's approximately normal, and that is the sampling distribution of X bar is going to be approximately normal for this sample. They're wanting us to find the probability that the mean playtime is more than 240 seconds. Before I can actually do that, I need to find the mean and the standard deviation of this particular sampling distribution. So the mean is going to be the same thing as the population mean, but the standard deviation, I have to use this formula if the 10% condition applies. So let's think through that. We have 36 songs. That's the sample size. And that definitely is less than all the, 10% of his whole population, because they told us that there was 10,000 songs on the iPad. So the 10% condition is met, which means I'm allowed to use this formula. So I'm going to do 60 divided by the square root of 36, which is kind of convenient. I get 10 seconds for my standard deviation. Now that I have my mean and my standard deviation, I can do a normal calculation. I've already written the proof for why I can do that because of the CLT. There's my labeled curve. They said has a mean greater than 240. So of course, yet again, we'll use the Staplet, normal CDF on your calculator, find a z-score, use the table. You're going to end up getting 0.0668. there is about a 6.68% probability. And then again, I usually like to go back to the prompt and just copy it down so that the mean play time is more than 240 seconds. There you go. Lastly, let's take a look at number 61. Sorry that this is a little bit hard to read. In response to the increasing weight of airline passengers, the FAA told airlines to assume passengers average 190 pounds in the summer, including clothes and carry-on baggage. But they didn't specify a standard deviation, and obviously passengers vary. A reasonable standard deviation is 35 pounds, so that's kind of what we're working with here, assuming that these are the mean and the standard deviations for the entire population. Weights are not normally distributed, especially when the population includes both men and women, but they are not very non-normal. A commuter plane carries 30 passengers. So part A says, explain why you cannot calculate the probability that a randomly selected passenger weighs more than 200 pounds. All right, here's the deal. Do you notice that there's no X bar here? There's no N, like there's no sample size, there's no X bar. This particular question is not talking about a sample, it's talking about the population itself. And we were told that the population is not normal. And so we can't find a probability. We can really only find a probability if the thing that we're working with, whether it is a population or a sampling distribution, the only way we can find a probability is if it is normal or approximately normal. So since we're not talking about these things, that means we're talking about the population in this problem. They're just pulling one person from the population. They're not like trying to do some kind of average. And the population wasn't normal, so we can't do anything. Now, part B, however, find the probability the total weight of 30 random selected people exceeds 6,000 pounds. And we need to show the work. They did give us a nice little hint there that to apply the central limit theorem, we have to restate the problem in terms of mean weight. Okay. Let's break this down. We are talking about the sampling distribution because we're talking about an X bar here. So I can say the sampling distribution of X bar is approximately normal because N is greater than or equal to 30. And I can say so by something about by the CLT, like that makes the sampling distribution approximately normal. So then I can use my formulas, or at least some of them. The mean is going to be 190 because that's just the mean of the population. I can't find the standard deviation yet because I need to check the 10% condition. So 10% condition tells me that the sample size has to be less than or equal to 10% of all the population. So this would be like all passengers on the airline, like not that particular plane, but just like in general, like all passengers. So this is going to be true. And so because that is true, I can find the standard deviation, which is going to look like this. And I get 0.05901, and we're talking about pounds here. Please don't forget your units. the mean was pounds, the standard deviation is going to be pounds. Now, I have stated that it's normal. I have found the 10% condition, and now I have the mean and the standard deviation, so I can actually do a calculation. So all that stuff combined allows me to do this properly. Now we might actually need to think for a second here. It said, the question, if I go back to the question, it said, find the probability that the total weight exceeds 6,000 pounds. So if the total weight exceeded 6,000 pounds, that would mean that like every person, or like the average would be more than 2,000. So if I have 6,000 total pounds, and I am talking about 30 passengers, I'm saying that the average, that X bar, is greater than 200 pounds. Like, that's another way of looking at this question. Because obviously if I put 6,000 in here, it wouldn't make sense. I honestly don't want to change this. I don't want to like have to combine means and standard deviations 30 times either, because, you know, then we'd have to actually add the variances 30 times to get the new mean and the new standard deviation. So it's easier just instead to like change the problem to a mean instead of a total. So I do my good old, I keep saying the same thing, the Stablet or normal CDF, or find a z-score and plug it into, or look it up in the table. You're going to get 0.0588, and I will answer in a complete sentence. There is about a 5.88% probability that the mean weight exceeds 200 pounds.